So now let's look at another thing we can do with the coefficients in these balanced equations. When we are working with all gases, we can combine the information from the balanced equation with what we learned about STP and gases. 22.4 liters is 1 mole of any gas at STP. So at any other temperature and pressure conditions, then equal moles of any gas will have equal volumes. If gases all have the same volume and we've given a number to it at STP, it follows that at any other temperature and pressure conditions, they would still have the same volume. It would just be a different number, right? So we can think of this as these coefficients in the balanced equations now representing liters or milliliters. So if we look at this balanced equation, which is not balanced yet, for the formation of ammonia gas, we're going to put a 2 here for ammonia. Now I have 6 hydrogens, so I need a 3 here. So now, how many liters of ammonia can be made from 2.5 liters of nitrogen? Well, I want my answer in liters of ammonia. So I look at this and I say, well, 2 liters of ammonia needs 1 liter of nitrogen, and I have 2.5 liters of nitrogen, so I can make 5 liters of ammonia. So I think these examples are pretty straightforward looking because we're looking at the mole-to-mole ratio or the liter-to-liter ratio. And we just look at the numbers in the balanced equation. But you know from everyday life that measuring moles or measuring liters isn't that easy. When we go in the lab and do our measuring, what kind of units are we usually measuring in? What are we measuring back there? We measure milliliters or volume of things. And what else do we measure if we're not measuring volume? Mass. And so it's a lot easier to measure the mass of things because you can't measure one molecule very easily. So we say, well, we measure groups of molecules in moles, but we don't count out the molecules to know it's a mole. We can look at the mass and use molar mass. So this next section is going to look at adding molar mass to these calculations so that we can convert mass into moles, then look at the mole-to-mole ratio, and then look at the mole-to-mass ratio to do a complete stoichiometry problem. So let's look at an example. How many grams of aluminum are needed to use 14.4 grams of ferrous oxide or iron 2 oxide? Okay, we look at this equation, and what is the first thing you've learned to do? Balance the equation. So we look at this, it is not balanced. I start with the most complex thing, the aluminum oxide. 2 aluminums, only 1 here. 2 aluminums. Now let's look at irons alone, so we'll do that last because we can fix that without monkeying up anything else. 3 oxygens, 1 oxygen. So I put a 3 in front of the iron 2 oxide. Now I have 3 irons, 1 iron, so I put a 3 there. Now if I'm going to need to use the molar mass to change moles into grams, the next thing I do is to grab my periodic chart and then I figure out the molar mass of the things of interest. So what are the 2 things of interest? Well, I want my answer in grams of aluminum, so I'm going to need the molar mass of aluminum. I looked that up on the chart. It's 26.981538 grams per mole for aluminum. And I have information about grams of the ferrous oxide, so I calculate that. That is 71.8444 grams per mole. Now I can go ahead and do my calculations. I want my answer in grams of aluminum. So what does it make sense to start with? Aluminum, the molar mass of aluminum. So I start with that, 26.981538 grams of aluminum is 1 mole of aluminum. Now I need to get rid of moles of aluminum. So when I think about what information I have, I can look at the mole-to-mole ratio of the aluminum and the ferrous oxide. So from my balanced equation, 2 moles of aluminum uses 3 moles of ferrous oxide. So I've canceled my moles of aluminum. Now I have to get rid of the moles of ferrous oxide, and I can do that using the molar mass. 1 mole of ferrous oxide is 71.8444 grams of ferrous oxide. And now I know that in the problem I had 14.4 grams of ferrous oxide. So I have 3.58 grams of aluminum is what I need to make the required amount of ferrous oxide. So when you think of this in terms of sort of the steps you're taking, you're given grams of one thing, we use the molar mass to get moles of that thing, then we look at the mole-to-mole ratio, and then we end up with the grams of the material we want. And again, I like to kind of go backwards by starting with the mass of the things I want. Okay, let's look at the one on the next page. How many grams of aluminum, is that the same problem? Of aluminum oxide can be made from that 14.4 grams of ferrous oxide. So how do we do this one? Where do I start? Molar mass. So we look up the molar mass of aluminum oxide, 101.9613 grams per mole. We already have our balanced equation because we're working with that same balanced equation from the previous problem. So we start with our molar mass, 101.9613 grams of ferrous oxide. No, that's not right. That's the aluminum oxide. We start with our grams of aluminum oxide, 101.9613 grams of aluminum oxide is 1 mole of aluminum oxide. So now I want to get rid of the moles. From my balanced equation, 1 mole of aluminum oxide is 3 moles of ferrous oxide. So I've gotten rid of the moles of aluminum oxide. Now 1 mole of ferrous oxide has a mass of 71.8444 grams. And I have 14.4 grams of ferrous oxide. So I get 6.81 grams of ferrous oxide. So we use molar mass to change grams into moles, and we use the mole-to-mole ratio from the balanced equation to change moles of one component, whether it's a compound or an element, into moles of the other component of interest. And we can only compare 2 things at once. Okay, you cannot have multiple comparisons in one calculation. All right, let's have you go ahead and do the next one at the boards with your groups.